Good morning, everybody. So this is an update from our last year's work. So we've talked a lot about the circuit designs using neuromemberistive computing paradigm in the last year's talk. So this year we want to focus more on the application landscape of these systems. So just to give a quick overview of what neuromemberistive systems are, these are neuro-inspired CMOS memristor hybrid systems. The approach is slightly different from the traditional MEADS approach of neuromorphic. It is more application driven. We focus on top-down design. The design methodology itself could be mixed, top-down or bottom-up, but from a high level it is application driven, and we abstract the computational principles, biological computational principles, not mimic them. And we also imbibe some roles of the subcortical brain regions. However, in today's talk, I'm not going to focus as much on some of the circuits we've designed for these different learning rules or the subcortical regions. The focus is more on the application spectrum. So this, let me try that. Here shows a high-level overview of how we work with researchers from neuroscience and psychology who give us guidance on the operating principles, and we work with machine intelligence or machine learning folks from Rochester Institute of Technology itself who give us on the inputs on the algorithms, and our expertise is on the integrated circuit and architecture design. So we could build simple hierarchical systems here. This is my student's CAD Dwight. Like if you give an input something like this, you just abstract those features, use low-level feature detectors, and build higher-level concepts and have a hypothesis whether it is a cat or something else. So if we really have to compare where these kind of systems shine compared to traditional conventional compute storage systems, I do not have exact numbers. This is based on more of the different applications we have looked at, and this is something that is really required for this community, I think, to have benchmarks in this spectrum. But if we look at these parameters which are really of interest, one is the energy efficiency. If you look at traditional systems, data and storage processing are performed on different substrates, so there is a lot of overhead in processing information or in relaying information back and forth, whereas in neuromemristic or neuromorphic systems, it is performed on the same physical substrate, so the efficiency is much higher. And compared to traditional compute storage systems, which are immutable, the plasticity is higher in neuromemristic systems. And currently, the scalability of these systems is not better than the compute storage systems, and perhaps it's in its infancy. So probably we'll have better scalable systems in the future. And applicability of these systems is really restricted. I mean, this might raise a lot of questions that there is a significant difference in applicability of these systems, but applicability in the context of several parameters, including the performance, I think we don't have a good grasp on where these systems really shine still. So that's why there is a significant gap there. So in general, these neuromemristic systems will shine where there is, we have a lot of noisy data, and the prediction or the precision rates are pretty relaxed. And the core component that we are using here is the memristors. As probably many of you are already aware, this is just a two-terminal device with state-dependent Ohm's law. And this is the classic symbol, and the hysteresis showing the memristive behavior in its on and off states. So there are several classes of these devices, and we've worked with several device topologies itself. So there are a few metrics that we think are really important for the neuromemristic systems. One is the dynamic range, the number of states, the retention, like how long you can retain your data, the energy, and the endurance. So I have the comparison with traditional flash technology versus some of the variations of memristors using phase change memory or STT-RAM or RRAM, and some of the target values we think are required for the neuromemristor system design. So you could see that in most of these cases, resistive RAM is doing really well. And I guess the energy is picojoules per bit is like the target is 0.01. I think we're still not there, but I think with advanced processing technologies, I think we'll be there pretty soon. And a quick overview on the device landscape itself. At a high level, we classify the memristive devices into the chemical and physical layers, and then within the chemical it's just like a metal insulator, metal layer, and we have anion and cation devices within which there are again several subclassifications. So we have worked with devices in this range, which is the bipolar nonlinear and the bipolar linear devices. So we worked with titanium, hafnium, copper oxide, and with silver and which are more like CB-RAM devices, and these devices are more stochastic in nature. And more recently, we are also looking at, with our collaborators who are designing the ferroelectric devices. So we think each of these devices excel for different applications. For example, in this case, it has a very high stochastic nature. So we exploit that stochastic nature in our computation when we are building the circuits and systems from there. So why how we are really using these memristors in neuromemristive systems, or in, I think, in a lot of neuromorphic systems, is the key focus is on using these as synapses. So here is a biological synapse and the corresponding memristor synapse. I mean, some of the neuroscience folks might cringe looking at this simplified representation, but we're just trying to show that there is this action potential which is coming in, the neurotransmitters are released, and then the gates are open, and there is this postsynaptic either excitatory or inhibitory potentials that are occurring. So similarly here we have potential that is changing or allowing a conductive path from one of the metal to the other, and then these defects you could almost think of, I mean, you could, depending on what device we are using, either it's a formation of a filament, so you could think of the variation of these defects enabling that connection. So in simplicity, we could think of using this single device to represent a synapse. I don't know if you can clearly see this, but this is one of our simple synapse implementation, but when we are actually implementing this, we have two of these synapses, not a single one, and it's basically dividing the current, and the ratio of that conductance here shows whether it's an inhibitory or excitatory connection. And you could have both a bipolar weight range, in other words, positive to negative weight range. So we have, I think, 1 to -1 in this case, so using this kind of design. So basically, it's small footprint and simple structure is what enables the high density, and still there is not a very, I think, there is not a good consensus on some of these defect formations itself in the devices, and it's an ongoing work. So it's probably redundant, but just to simplify the idea of using these memristors, we use it for synaptic functions because they provide physical interconnect, and they modulate the signals, and the other thing is basically they facilitate adaptation or learning by how you are controlling the weight states within that device. So since this device provides all three in one medium, it is an excellent choice to implement for synapses, but we also use these devices to implement neurons and other functions within our neuromemristive systems. Okay, so that's a brief overview of the memristors and the neuromemristive systems. So let's dive into the application landscape. So we've explored quite a few application domains, and I I tried to minimize the use of circuits in this, but show like in the overall context what kind of accuracies we are getting for these different applications. So the first application we're going to look at is epileptic seizure detection. Epileptic seizure is a chronic disorder of the central nervous system. 1 in 26 people will develop this disorder at some time in their life. So most often we use EEG signals to detect epileptic seizure. So the use cases we are thinking of how we could use this is as an early alert system to preclude any unwanted exertion, or control delivery of drugs to reduce side effects. Perhaps this is a long way out there, but basically as an early alert system. So for our initial framework, we used the algorithm or the topology by perhaps most of you are familiar with from the computational side is the reservoir framework from Jaeger's group, where we have a time series spike or spike rate as input, whereas here in this case it's a normal signal versus a seizure signal and a processed input, and here is the reservoir, which is just nodes with random weights, and then an output layer which could be a simple linear regression layer. So in our case, you could also think of this as a partially trained ANN with a recurrent network topology, but in our case we use some memristive circuits or designs or synapses in this output layer, not actually in here. We just used simple resistive models to represent that reservoir. So closer look on the hardware. So that was a model that we used at a high level, but looking at the hardware itself. So we started off at the topology. What are the topologies we want to look at? We use two different topologies in this design. One is a random and ring, the other is a ring topology. So the random topology, as the name suggests, the nodes are randomly connected with varied degree of connectivity. And when you realize this in hardware, so this is the reservoir I'm talking about, and when you realize this in hardware, the architecture is much more dense because of the higher degree of connectivity in this implementation. So we wanted to look at low degree of connectivity systems, and the ring topology is a simple structure where each node is connected to two of its adjacent nodes, and it's obviously because of that simple connectivity, it's very easily realizable in hardware. So from there, once we identified the topologies we want to work with, then we actually build the architectural realization. So you could think of this neuron box similar to a configurable logic block. So all the neurons and its associated synapses are in this box. And again, the implementations of the neurons and synapses are in here. We have a different implementation for excitatory and inhibitory synapses in here. And the muxes are used to route signals to pre-specified paths. So if you look at the ring topology, this is how it's like a 2D structure, neuronal array. It looks like it's reconfigurable, and you could imagine if I use a random topology in this, it gets a little denser because of the connectivity. And putting this all together, this is our framework for the seizure detection. So we are having the input signal and some pre-processing stage, which is a normalizing stage, and the actual realization of the reservoir and the output neuron, and some post-processing. Basically, the output neuron is looking for a threshold. So this is the output we see at the reservoir. So you could see that I think the threshold was somewhere here. Most of the signals are above the threshold. And the accuracy we got was about 97%. And we compared it with a software implementation that was done by a group in Europe, and they had about 98% accuracy. Traditional software-based systems for epileptic seizure detection have 99% accuracy, but I think we did pretty good here. But I have to be honest, we did not include all of the variations of the devices in this implementation. So our next step is to implement all the variations and different models of the actual variations to see how the accuracy looks like. Okay, the second application I'm going to look at is the speech emotion recognition. So here we want to recognize the emotional state of a human based on speech, and it could be useful in HCI. So, and also it is much simpler to realize in hardware, to be honest, so that's one of the reasons we chose this application. And the database we used here is the Berlin database for emotional speech, and they have 10 different daily German sentences, and I do not speak or understand German, so if you just see, you can see, I don't know if you can hear, probably not, sorry.
Der Lappen liegt auf dem Eisschrank.
I don't know if any of you understand.
Der Lappen liegt auf dem Eisschrank.
So it's just showing like the neutral and anger. So in this case, we just show those two. Pretty angry person. So we had to do some pre-processing. So we used a feature extractor. We extract all the desired components for emotional information. We just used an 8-bit, 8 mil filter bands, and that's the circuit. So we just used some fast Fourier transforms and got the 8 bands. And from there, if we look at the actual output of this feature extractor, this is for the neutral and this is for the angry emotion. So you could see that from band 3 to 8, sorry, in the neutral, there is not much happening. You could see a clear distinction in the angry mode. So from there, we use this and implement it in the similar framework as I've shown earlier for the epileptic seizure detection. So we wanted to see what is an optimal size of the reservoir for this kind of implementation, and so we played around quite a bit to look at what's the optimal size, and I think we identified that 190, I don't know if you can see here, sorry, 190 is the optimal size for the reservoir, and from there we identified what is, for this reservoir size, what is the optimal learning rate, and I think we got 0.25 as a good learning rate, and the connectivity in this reservoir is about 20%, so which is ideal for hardware realization. And so the accuracy for this is about 96%, and we are still testing for other emotions how the accuracy is affected. And again, state-of-the-art systems have 98% or 99% accuracy, so I think it's still really good compared to looking that it is implemented in a hardware. And the third one in this set is the speech recognition. So here what we wanted to do was actually take the real device limitations into consideration and see how the accuracy of the system varies. So this is the device that we got from the Air Force Research Labs. It's a copper oxide memristor, so the switching is not, so here is the ideal memristor behavior, and you could see that the device model is like, just we have those two states. So it's not what ideal model, but we could, we could use it for our implementation in a sense. You could have a limited weight states in this kind of implementation. So we try to use it for recognizing speech and then see that the accuracy is not as good as the emotion recognition or the seizure detection. We were in 80% and then we reached up to 90% or so. But the interesting thing is the power consumption of this system is much lower compared to traditional implementations of speech recognition, and so I don't know if you could clearly see that we have static and dynamic power for two different cases. One is the regular implementation and the other one is more optimized implementation where you see a lower bars here is for the subthreshold implementation. So we have about 10 nanoamps in here, or like much lower power dissipation, and obviously you could see as you increase the reservoir size or the degree of connectivity, this kind of grows significantly, not significantly, probably more linearly. And this is just showing the confusion matrices showing that we have pretty good accuracy on there. So now shifting to other applications we are looking at. A very simple one is the visual feature detection. So here we are trying to model processes in the early visual system where simple features are being extracted, such as edges. So this is an extreme learning machine design that we have used, and you could see that we have used different kinds of neuron designs here. So these are the linear neurons at the input layer, and the output and the hidden layer are the sigmoidal neurons, and we use the memristive synapses in this design. And so this is our output for the edge detection, or you could think of it as a simple coincidence detection, and you could see that there is a lot of this noise, and adjusting some of the parameters with the memristor, I think we could get a cleaner realization of this. But I think this is still good because it is not getting stuck in a local minima, I think. So we're able to detect edges using that. And then one of the key components that is used in most of our realizations and is linear regression. So for example, in the reservoir node, the output is a simple linear regression that we used. So we try to build custom hardware for linear and logistic regression, and we've used different algorithms to implement that. So one is a stochastic least mean square, which is an algorithm developed in our lab. And so it is exploiting basically the stochasticity of the device to implement the algorithm. And so the performance of this algorithm is pretty close to what a traditional least mean square algorithm looks like. So you could see the MSE. And similarly for MNIST classification, we've seen similar matching from the stochastic LMS to the least mean square. So the advantage of exploiting this stochasticity is not only that you are using the inherent device characteristics to your advantage, but also it reduces the overall implementation cost in terms of area. So in here we have about 3x reduction in area when we are using the stochastic implementation, particularly because multiplication is very expensive when we are trying to implement in hardware. So using the stochastic version really gave us advantage in reducing that. The next one is more target classification. So I know yesterday someone said Caltech is a very simple database, really, really simple database, but for hardware designers, this is a complex database to work with in trying to get the accuracy. So we use this data set to do some target classification. So we did some pre-processing, which is just conversion to grayscale, and so we also fixed the size to 60 by 60 pixels and used simple dimensionality reduction using LPP, which is locality preserving projection. So with that you could think of it like some kind of PCA and principal component analysis to extract the important features and feed it into the hardware realization, which is a neuromemristive system here. So it's just nothing but a winner-take-all circuit. So in this, you might really frown at the classification accuracy. So we did not get pretty good accuracies here. So the training is pretty decent, 60% or something, but the test accuracies are in 27% or something. But we compared this with SVM, and I think the performance is similar. So it's just in general that it's a hard data set for hardware. I think it's pretty good that the layer itself is a single layer, so I think the performance is still good for that. So we are still looking at optimizing this realization now. So we wanted to look at what are the area costs when we increase the output dimensions of this kind of system. So the x-axis shows the dimensions and the y-axis shows the number of neurons or synapses you need to implement something like that. So you could see that there is a linear increase as you increase the number of dimensions in the synapses and neurons. So what we did, the dimensionality reduction technique we used reduced the dimensions from 3,600 to 100. So we got a significant reduction in the size. Of course, it affects the classification accuracy too. So one of the significant challenges when we are realizing these systems in hardware is the training process and the debate whether we want to do it on-chip or off-chip. On-chip training is desirable, but it is very expensive. So we looked at how we could overcome this challenge of realizing complex resilient backpropagation algorithms, training for these systems on chip. So we first tested for a simple implementation using, I think this is MNIST data set, a raw image and an averaged image. And this is our implementation for the neuromemristive system. It's an MLP. And you could see that we used both linear and sigmoidal neurons and just used a one-hot output at the end. So the classification accuracy for this one, you could see is around, I think, 85% or so. Not great compared to traditional accuracies you get for this. And then we have this idea, we presented initial results from this in the last year's talk, but the idea here is to perform part of the learning on chip and part of it off chip. So for example, we identify the training algorithm we want to go with for the resilient backpropagation, let's say, and then do the ideal model of the system with off-chip training and transfer certain selective features on chip. So what those features should be is again a challenge, and it also depends on the specific algorithm. So in this case, we transferred the features like the weight and the state, and then we use the on-chip variations for both CMOS and memristors that feed into the system because it's an on-chip learning system. So this model has given us pretty good accuracies. So I show here two different kinds of parameters that are transferred from off-chip to on-chip. One is the weight programming and the other is feature training. In the weight programming, there is no hardware training involved, whereas in the feature training, we do hardware training. And if you look at the accuracies for the ideal model, as I showed in the previous slide, it was in the 80s. And then when we are looking at the feature training, we pretty much got pretty good accuracy compared to that model. And these are, again, how the area is increasing based on different models that we are using. And we had varying or reduced area size, in this case accuracy versus the unit area for these two. Okay. Sorry, so I'll run through this. Last application is countermeasures for power attacks. So we've been using performing this with different algorithms before, but our most recent focus was using Ketchuk algorithm for SHA-3. So we've recently just had attack points identified for single trace and multiple traces, and we were successfully able to do the correlation power analysis attack on this system, where the correlation shows what the values for that, whether it's a logic 0 or logic 1 for that system. So we are trying to use the neuromemristive system as a countermeasure for these attacks. So the first step was to build this attack framework, and the next step was to use the neuromemristive system as a countermeasure. And we are still building for that, but we just tested with an S-box, and we were successfully able to use this as a countermeasure attack where we couldn't identify the successful keys guessed. So we still are trying to use that for the Ketchuk model. So that's a work in progress. So looking forward, all the models and architectures I've shown are embedded in small-scale systems. So there are some limitations when we are looking at large-scale systems, particularly the simulation complexity. It takes at least 2 days to run some of these single runs, so it is really hard. And we cannot, right now, I think all these models are abstracted. A lot of these things like potential synapses or dendritic computations, a lot of those things are not inbuilt in our designs. And the other important thing is whether the nature versus nurture. So in traditional systems, you have an inbuilt, the evolutionary process give you an inbuilt features, and then you nurture those to build stronger connections. So how do we actually realize that kind of behavior in hardware is yet to be seen. And the biggest problem we find is that there are no good standard metrics, and I think Karl-Heinz's group is working on building some of those metrics, and hopefully we'll be able to use them in comparison the systems with classical systems. So I think the most important thing for us as hardware designers is to accept what our limits are, and then I think we can try to go beyond them. And I think that's the first phase, and I think we are at a stage where we identify a lot of limitations of the hardware, and probably a lot of you might have seen this from Dr. Nicolelis's group, so the future looks bright. And these are the students who helped design these things, and I thank my sponsors for
We're running a bit late, but there's one question real quick while we switch speakers.
So could you comment on performance and power comparisons to more traditional hardware, CPUs or?
Yeah, sorry. So the performance is a bottleneck still with the implementations we have. Power or energy efficiency is the single significant advantage we are seeing in these systems. So anywhere from 3 to 10 orders depending on the kind of implementation we are using. So that is really the motivating factor.
10 orders of magnitude?
What is it?
10 orders of magnitude more efficient?
In some very optimized cases. So I should say in general it is 3 orders of magnitude is what we are seeing.
All right, thanks, Dhireesha.